Now that we have seen what convex functions are, let us take a look at which operations preserve convexity. So first of all, let's notice that we have defined convex functions as functions which take values in the extended real line, so they are allowed to take plus and minus infinity as values. And we will see that we don't lose or gain anything over taking real valued functions, and that is the first theorem I will formulate here. Theorem. Okay, so assume that C is a subset of our finite dimensional inner product space, and let's assume that this subset is convex. And let us also assume that we have a function f tilde defined on C with real values. So this would be a classical real valued function and defined on a subset of the whole space. And let this function be convex on C. This means that the convexity assumptions holds for all, the convexity assumption, like this inequality, holds for all points in C. I will not write this explicitly here. But then we can define a new function. So we can define f defined on the whole space with extended real values. And this is defined by taking, well, f tilde of x whenever this is defined, so for x in C, and plus infinity otherwise for x which are not in C, is a convex function in the sense we had defined in the last video. Okay, so whenever we have something which is defined on a convex subset and is convex there, then we can extend the definition to the whole space by taking plus infinity for the other values. So, and conversely, if f is defined in the whole space with extended real values, and we have to assume, which we will assume usually anyway, that we don't take the value minus infinity for any let's write it like this, for any x in H, then the set dom f, which is called the effective domain, so, and it is defined as the set of all x's where f of x is less than plus infinity. I call it the effective domain of f, is convex. And now we can go back. We can, here we took f restricted to a convex subset, and now as we have a function which is defined on the whole space, we can restrict it to the domain where it takes finite values. And so we can define f tilde on dom f, and it takes real values, and we define it as just this, and it's restricted to dom f. So it's of this form with C equal to dom f. Is convex on dom f. Let me just check that I have everything. Yes, looks good. Let's prove. Okay, so we have to prove the convexity of this. So first of all, let's go from f tilde to f. So given f tilde, show properties for f. And we have to show that this function is convex, which is we have already seen in the definition of indicator functions, and we have shown the convexity of indicator functions of convex sets. So as in the proof of the convexity of indicator functions of 3 times off in the sentence of convex sets, it suffices to show convexity on dom f. So whenever the value is the value of f is plus infinity on the right hand side, on one of the points in the right hand side, then obviously we have to show that something on the left hand side is less or equal than plus infinity, and that's always the case. Everything is less or equal than plus infinity. So it suffices to show convexity on dom f. So, but this is actually C. So there is nothing to prove because convexity on C is already assumed. Which is the assumption on f tilde. So there is not much to be done. Let's go from f to f tilde. So given this function f, which is defined on the whole space, we have to show that the effective domain is convex. So let x and y be in dom f, and lambda between 0 and 1. Then we have that f of x and f of y are both less than plus infinity, and therefore they take real values, which is not important to the convexity here. And by convexity, so f of 1 minus lambda x plus lambda y is less or equal than 1 minus lambda f of x plus lambda f of y. F of x is less than plus infinity, f of y is less than plus infinity, and therefore the whole thing is less than plus infinity. And so we have 1 minus lambda x plus lambda y in the domain of f. So this shows that the domain of f is a convex set. And now convexity on the whole space is a stronger property than just convexity restricted to a subset. So what we have to show here is that this restricted function is convex on dom f, which is automatic from convexity on the whole space. So the only thing we have actually shown here is that the domain of f, the set of all points where f is less than plus infinity, is convex. And since I don't know if this sentence that convexity on the whole space is stronger than convexity on DOM F fits on this frame, I just conclude the proof here. Okay. So now we have seen whenever we have a real valued convex function which is restricted to a subset, we can construct a new convex function defined on the whole space by extending it to plus infinity. Okay, now let's see what else we have. So this is in a lot of parts parallel to the convexity-preserving operations for convex sets, as we will see. So let Fi I in I. So I is an index set. Fi should be convex functions. So Fi I in I. B should be a family of convex functions, and Fi should be defined on H with extended real values. Then the pointwise supremum, and we write this as sup Fi with I in I. And this is a function defined on H with extended real values. And this pointwise supremum is defined as sup Fi. This is a function. This is a new function. And whenever we want to find the value at the point x, we set this, as you can imagine from pointwise supremum, we take Fi of x, and we take the supremum of these values over I in I. Okay? So by definition here, it doesn't matter if you set the parentheses here or here. And then the pointwise supremum is also convex. Why is that? Notice the similarity, by the way, to the to convex sets, where we showed that the intersection of an arbitrary family of convex sets is convex. Okay, proof. What we have to prove convexity. So let x and I be in H, and lambda between 0 and 1. So by convexity of any member of this family, we have without supremum, we have Fi of 1 minus lambda x plus lambda y less or equal than 1 minus lambda Fi of x plus lambda Fi of y, convexity of Fi. And therefore, if we take the supremum on the left-hand side, we preserve this inequality. So supremum I in I, Fi of 1 minus lambda x plus lambda y is less or equal than supremum I in I, and here we take 1 minus lambda Fi of x plus lambda Fi of y. Okay. Now for the supremum, if you have a supremum of the sum, then this is always less or equal than if you split up the sum and take the suprema of both summons separately. So what I mean is that you can write less or equal than supremum I in I, and here you take 1 minus lambda Fi of x parentheses plus supremum I in I lambda fi of y. So why is that? So here you take the supremum, and you have to take the same I in both summons, because there is only one instance where you can choose I. And here you can take the supremum for the I for the first coefficient, the supremum of I for the second coefficient, and they can be different. And this, since you have more freedom in taking the supremum, this is less. You have this less or equal between only one supremum, less freedom, in contrast to two suprema, more freedom. Okay, and this generally holds for suprema. Okay, and now you can pull out these real numbers here. These, by the way, non-negative real numbers, and this is 1 minus lambda supremum I and I fi of x plus lambda supremum I and I fi of y. The only thing which we have to talk about would be if the supremum here is plus infinity, and possibly this 1 minus lambda. Well, whoa, that does not belong here. 1 minus lambda is 0. And in this case, you multiply 0 with plus infinity, and here you have a supremum of a lot of zeros, might also be plus infinity. And in order to just tell the truth here, whenever you have a lot of finite values here, which you multiply with 0, then you get 0 for the supremum. Here you might get 0 times plus infinity, which we have set to be plus infinity. So actually you have to write less or equal here, and I just write a remark. So this is because of 0 times plus infinity, which can be a problem here, but the problem goes in the right direction, so it's not a problem for our proof. Okay, same, by the way, goes here. And then now we have shown convexity of this supremum. So if you set the parentheses accordingly, like if you set this the parentheses here and the parentheses here, which you can, because setting the parentheses here doesn't matter, then you have shown convexity of the supremum, which concludes our proof. And the last theorem I will state without proof, because does not fit into the frame of this video probably. So has 3 parts. The sum, and here I mean the pointwise sum, f1 plus f2, and this should be defined just as I said, pointwise sum of 2 convex functions is convex. B for lambda greater or equal than 0, just a real number, and f defined on H to R bar convex, the pointwise multiple lambda f, and if you if you evaluate this at x, then you get lambda f of x is convex. Notice that it is very important that lambda is not non-negative, because, for example, the absolute value function is convex, but minus the absolute value function is not convex. And C, for a convex function defined on H, and a linear operator L defined on H with values in G, the function actually if you have a second space here, so you have G. So the function f is defined on G with extended real values, and L is defined on H with values in G. And the function f composed with L is then, so L, you take values in H, L maps them to G, and then f maps them to R bar. And this is obviously the usual function composition. So yeah. Okay, L should be linear. I should have said that. So for the composition of a convex function with a linear operator is convex. Okay, and just give me a final remark. I give you a final remark on point B. If you multiply a function with 0, then you get the indicator function of its effective domain. Why is that? If f of x is equal to plus infinity, if you multiply this with 0, then you get plus infinity by definition of our operations, and therefore you get plus infinity also here, and therefore you have to take the effective domain of f. So 0 times f is not 0; it's the it's the indicator function of the effective domain of f. And if you take care of that, then you're okay. So we have seen basically 5 different operations to get new convex functions from other convex functions.